Other topics.
In progress.
Sure, absolutely. A topic that, like many others, has suddenly become very hot in both computer science and machine learning. Although, as I'll walk in the first part of the presentation, essentially you will see that people have been doing online optimization, and in many cases distributed online optimization, for many specific problems for the last 50 years or even longer. So what I decided to do is we give a high-level overview of how to formulate the problem, some key issues, performance metrics, and a very light touch on algorithms. And then in the second part, somewhere here, I'm going to post some semi-open problems, and then some of our recent work that is trying sort of to say something about these open problems, and then conclude with some open directions for people in the audience that are interested. Okay, so online optimization is essentially about, at a high level, sequential decision making, and a lot of these applications, as I pointed out, have been around for a long time. And many of you may have contributed both algorithms and problem formulations in a whole bunch of these areas. Something fairly new that has driven a lot of the developments, that's why I said that suddenly has become really hot in broadly computer science, machine learning, artificial intelligence, data science, pick your favorite description, is sort of deep learning, where they're trying sort of to use a lot of these distributed algorithms to train very, very big models. We had a presentation before lunch on selecting the learning rate and so on and so forth for deep learning models. Okay, so some of the key components is, again, all these are fairly known to many of you in the audience. Describe the decision maker, the cost reward function, and something about the environments. And again, at a high level, hand waving, no math yet. So the decision maker, or in learning theory parlance, the learner, selects an action or a decision from a given decision set, and then either you incur some cost, again in learning theory you're going to call it regret, associated with this decision, and the state of the environment. So the problem is fairly general, and of course there are, as I already pointed out, specific sub-problems that you can go much, much deeper and say much more at this very general level. And of course, the decision maker's objective is to minimize its cumulative regret against the best fixed decision in hindsight. So you have some competitor, and we'll see how people define the competitor or the type of theoretical results that have been defined. And obviously, I've already mentioned that a couple of times. At this high level of generality, there is a very long history, both engineering problems, operations, research. Here is a very short list, where in some of these cases you have much, much more detailed structure. It's not just a generic problem with a cost or reward function. You have, you can say much, much more, like in the 80s and 90s, job shop scheduling. There was a lot of work on bandits going back in the 70s and 80s, and bandits, especially in some new forms with context, contextual bandits and so forth, have seen a renaissance over the last 10 years. Search games, and then other online matching algorithms, the good old secretary problem, which is kind of an optimal stopping rule type of problem, portfolio selection, linear search problems, and so on and so forth. I mean, the list goes on and on. There are a whole bunch of problems that at this level of generality have the flavor of sequential decision making. Okay. From a more algorithmic development, and again, from a more learning theory perspective, this is an excellent book. Elad Hazan at Princeton, and it's available online. So, you know, you do a Google search, you can download 200 pages, and he discusses a number of interesting problems. He's advertising that he's coming up with a second edition. So I have borrowed some of the basic notions from this book, but there are, unfortunately, there are no other good surveys. I find a lot of good surveys on online optimization, but this is from a centralized perspective. So you have one decision maker that has full information. So the problem starts becoming much more challenging and much more open when you get in distributed online optimization. Why do we want to do distributed algorithms? Okay, you take your pick. A good motivating example may be data privacy. For example, even in machine learning, I don't want to share or I cannot share the data with you. So I keep my data private, you keep your data private, but nevertheless, we would like either to learn a common model or improve my model, some sort of transfer learning. In some other cases, even if you don't have any issues with data privacy, you may have very large data sets that are stored across different databases. And therefore, essentially, you would like sort of to avoid a lot of latency by sending data around and so on and so forth. So it's much better to communicate models, parameters of the model, even if the model is kind of semi or non-parametric, like a deep learning model with millions of parameters, as we heard in a number of talks. But nevertheless, it may still be more efficient than sharing the data. And then, in principle, you can also start thinking about more adversarial settings. In the sense that as you have all these type of communications, you have powerful adversaries that are trying to either corrupt your data or mess up with information that you exchange. And therefore, the goal of distributed or decentralized algorithms, again, a topic in optimization theory that, I don't know, Panos knows the history, goes back, I don't know, 40, 50 years, depends on the flavor of the algorithm, is only to exchange local information from one of the decision makers and its own direct neighbors to achieve whatever objective they have, minimize a function subject to some constraints. All right, so let's start putting a little bit of notation. So essentially we have a sequence of cause, regret, objective functions, pick your favorite term depending on the literature that you're reading. And essentially, we're looking at univariate objectives, not multi-objective optimization. Actually, if you have multi-objective optimizations, the literature is essentially beyond sparse. I couldn't find anything. And essentially, we have n players, so capital N denotes the number of decision makers or agents or players, and n is the dimensionality of the decision variable. So that's why the function, you know, this is sort of domain, and this range of the function. And each function at time t has this form, essentially has the n arguments that are the local decision variables for decision maker I, and there are n of those. And in principle, the xi's take values in some set, which can be either an unconstrained, you can think of it as Rn, or a subset of Rn, depends on the type of constraints that you would like to incorporate. And we'll see how far the literature has gone in the presence of constraints, not in terms of sort of algorithm, but in terms of more establishing some theoretical results that are coming up later on. Okay. So what about our decision makers? They're organized in a network, and essentially they can communicate directly only with their immediate neighbors. In principle, nothing prevents you from having a complete graph. I can communicate with anybody else in the network, but this is going to start incurring high communication costs. So usually you have much more sparse topologies. And of course, you need to put a little bit of structure on the communication network because obviously it needs to be connected, but actually you need a little bit more structure if you want to do some theory. And we assume that the decision maker possesses private information. We're going to see later on, I have a couple of examples of what private information is meant in this context. It may be regarding the objective function. Everybody we're going to see later on is going to start breaking down, Or if you think, for example, from a machine learning type of application, I have my own data sets, and my objective function will be minimize some loss, square error loss, cross entropy loss, pick your favorite one. And then essentially, at each time step, the decision maker needs to make a decision which is feasible and based, and there are somewhere here we start having different flavors of the problem, either on partial or complete historical information, whether you have stored all the previous information for yourself and how much is communicated to from other decision makers. And essentially, subsequent, the environment, that's what people call it in this line of work, essentially reveals this type of information. After all the decisions at time t-1 have been made, essentially we have solved for xi, I goes from 1 to n, then the environment spits out the next value of the function and also the next set of constraints. And I've already said that the decision maker only interacts with whoever is connected to in the communication network. And essentially, these are finite horizon problems. Okay, so this gets us to what is the optimization objective. And so here, let me introduce, my notation is not the most mathematically kosher, because in some cases I interchange a little bit. So this is the global cost function at time t, and we assume that it's decomposed into n functions that are time varying. So each decision maker faces its own objective function or regret function, and it's specific to the agent. So therefore, essentially, we have this additive global cost function, and then there are various flavors of the problem. One of them is that is sort of consensus-based, and essentially we're trying sort of to optimize a global goal. And at the end of the day, we would like to optimize to solve this finite horizon problem, subject to a feasibility constraint. And as I mentioned, you can start incorporating more information. So this is the most vanilla and in some sense, the simplest form of the problem. And then you start having more complicated forms. This is a multi-agent coordination type of problem. You can solve it with similar algorithms, but when it comes to some type of theoretical results, here I missed the f of t, but in this particular case, each decision maker function is a function of all the arguments. So whereas before, your cost function is a function only of your decision variable, in a multi-agent coordination setting, your cost function, your personal cost function, is a function of all the decisions of the other agents as well. And the objective is the same, or essentially we're trying to optimize over a finite horizon. Actually, in this form, the notion of a non-cooperative game can be easily formulated. And in this case, every decision maker, here, the objective function becomes somewhat different because you're aiming to optimize your own objective function subject to, this is minus j, subject to all the decisions that all the other players in the game, the other decision makers have made. So it's x minus j. It means that you're trying to optimize your own objective subject to what all the other players have sort of decided. So then the next question is, if we were trying to solve any of these problems, this is sort of the most generic and in some sense the easiest to address, then what can we say depending on the type of functions that we're dealing with? And obviously, as we're dealing with optimization, a lot of work on convex functions for obvious reasons. They're much better behaved. You can leverage a lot of previous results from standard optimization theory. You can have much better results if you assume that the sequence of functions, both over time and for each agent are strongly convex and smooth. Right now, you have a lot of additional information. The reason that this may not be, it may not be, how to put it? It's nice mathematically, but it's easy sort of to start breaking down. Here is a much more general case. For example, even in machine learning problems, you have a loss function, think of least squares or square error loss. It's convex, but it may not be smooth because, for example, you may have a sparsity constraint, an L0 norm, or then of course you can do convex relaxations and so forth. So this is very interesting from a theoretical perspective. You know, if you want to prove the best results, you are working in this type of under these assumptions. And as you can see, a lot of the literature, at least coming from more computer science and taking this very general formulation of regret functions, is fairly recent. And if you start looking, and apart from some papers that showed up in SIAM Journal of Optimization, and also IEEE Transaction Automatic Control, everything else that if you start looking at this literature, you need to start looking at the machine learning or learning theory type of conference, ICML, primarily ICML, occasionally COLT, and so on and so forth. For whatever reason, this line of research has not penetrated other journals of optimization. For example, you're not going to find anything in mathematical programming. Don't ask me why, or So there is a lot of room for additional work. And as you can see, the non-convex case is very, very recently has been, people have started sort of attacking it. Algorithmically, of course, you can always throw a stochastic gradient type of algorithm, the algorithm that we use to train neural networks. But in order to be able to say something more, a lot of is missing from a theoretical perspective. So there is a lot of room for a lot of new innovative work. So what about constraints? In most instances, it's assumed that the constraint set is time invariant, or in some cases that all the agents have faced the same type of constraint. In many cases, essentially, this also captures the unconstrained problem. A lot of the problems, for example, if you're trying to optimize a machine learning type of model, even if it has kind of a sparsity constraint, you incorporate it through kind of a tuning parameter and Lagrange formulation, and essentially this becomes Rn. Or a subset of Rn. And for theoretical reasons, usually we assume that these sets to be compact in order to be able to prove results, or some of the results, or some of the strongest results. So you may say, okay, this starts sounding a little bit restrictive, but actually even in centralized online convex optimization, this was one of the papers that sort of started this stream of work. It was sort of necessary. Of course, if you make other assumptions on the strongly convex functions and also smoothness, then you can get rid of that type of constraint. The constraints can also be coupled. So essentially here you can start introducing either linear inequality constraints, very, very classical in optimization theory. This is sort of general type of formulation. But from a more theoretical perspective, people have not, we don't know much how these distributed algorithms behave. And I'll explain exactly what I mean of how they behave. We may know convergence properties, but we don't know how the regret grows as a function of time. Something of note, given the fact that my first slide said something about decision-making, sequential decision-making, where on earth are the dynamics? And that's why I put this slide. In this formulation, through all these functions and so forth, and this consensus optimization, where are sort of the dynamics? You may have some problem that has inherent dynamics, like some of the problems we saw before, online search problems and so on and so forth, or secretary problems, or bandit problems, and all of them are explicitly absent from the formulation. So in many cases, essentially, the way to think about those is through sort of the constraints. That's why I said that this is a very nice framework, very general framework. Interesting sort of to study what you can say about it. But on the other hand, if you can specify more structure, probably this is not the best framework to tackle a specific problem, because you have sort of to do a lot of gymnastics to incorporate a lot of additional information like dynamics. So here is a kind of a small detail. So what is the mental model when you postulate this framework that I previously described? Essentially, the environment, nature, or somebody, essentially has already decided the sequence of functions. And the only thing that happens at time t, after you make your decision, this function is revealed to you. So it doesn't have, so all the sequence here is predetermined before you even started doing anything with optimization. Nothing prevents you from having stochasticity as well. This is not exactly a deterministic setting. You can have your FIT also accommodate additional stochasticity because you may be in a random environment. That's perfectly fine. Easier said than done. In principle, you can consider an adaptive setting where after I have seen how we got to time t, for time t plus 1, nature decides to generate FIT. So in this case, essentially nature or whoever decides these functions and these constraints, observe your history. So it starts having a much more adversarial type of formulation, and very, very interesting, very, very open. Okay, what are sort of the performance metrics? This will come up in some of the theoretical results that I'm gonna briefly describe. So here is, again, this was a seminal paper because we start formulating this line of work. So let's consider a decision sequence, which is feasible. And essentially, the dynamic regret is, this is your comparator sequence. Somehow it was calculated. It may be a clever sequence of decisions, or it may be a stupid sequence of decisions. But essentially, the regret is how well you do over time. We have this finite horizon across all agents when we compare it with the performance of this comparator sequence. Of course, the name of the game is how well you're going to do if this sequence has some good property. So essentially, it's an optimizing sequence. Or in many cases, actually, because here you can do much, much more theory, and the first theoretical results were in this context, where essentially this is a stationary sequence. Essentially, you find the optimum by solving this type of problem, and then the comparator sequence never changes over time. Whereas this is sort of a dynamically evolving type of sequence. So again, this is, against, in some sense, worthy comparative, clever comparator sequences. So you're trying sort of to see how worse is sort of this gap. That's why I said a lot of the theoretical work is trying sort of to characterize how this difference, if you pick one of those, is growing as a function of the horizon. Why static regret? So essentially, I've already mentioned most of it. Assumes that the comparator sequence does not change over time, is theoretically attractive. It's the first thing that you can start analyzing. However, it may be fairly restrictive in practical streaming big data settings. So for example, if I was trying sort of to optimize in a machine learning model where sequentially frames within a video or the weights of a dynamic evolving network are revealed to me, and essentially I'm trying to do such a thing, obviously, I'm in a very variable environment, and therefore considering a static regret or the comparator sequence to be static, I can do sort of better. And then there are these versions of adaptive regret, and essentially what they focus on, and you'll see towards the end of the talk why I'm mentioning this. Again, theoretically, these are kind of interesting because essentially you consider a subset of the horizon instead of summing from 1 to t. Here you're only considering a subset of the horizon over a fixed time interval, from time 5 to time 15. You would like sort of do, or you try to minimize static regret over a continuous time interval. Again, very little analysis in this context. The first results have just started appearing in the literature. And for those of you that remember all the literature on bandits, in bandit type of problems, you were trying sort of to find optimal policies by formulating as a Markov decision problem. And there were two types of criteria, or maybe three types of criteria. One was discounted cost. So it had the flavor of sort of the regret, but you discount future observations. This has exactly the flavor of average reward in the bandit type of literature. And essentially, there is this recent paper proposed this following metric, but if you're trying sort of to understand what happens and how to optimize with respect to this criterion, essentially there is no work in the literature. So this is again another very open area. Apart from very specific results that go back 30, 40 years in the bandit literature. And as I mentioned, again, nothing prevents us from incorporating stochasticity, and therefore all these dynamic regret, static regret, you just take them with respect to expectation over distribution F of your random variables. Think of them as sort of noise. Okay, so this is at a very high level, the formulation of the problem and some of the key ingredients, what type of functions we are interested in, and what type of algorithms we're going to have, performance metrics, and a few things about the constraint. So let me walk you through some of the examples. Obviously, you can solve these problems with a lot of other techniques. You don't really need to put them in this framework, but this is kind of easy to visualize framework or easy to describe framework to see how all these pieces come together. So I have a network of M-square sensors, and I place them on a two-dimensional grid. So this is my two-dimensional grid. I grid this room, and I place M-square type of sensors on the lattice. And there is a slowly moving target somewhere here walking through the room. And essentially, as you can see, essentially is doing kind of an autoregressive type of random walk. Essentially, its new position is where it used to be, multiplied by certain metrics that dictates the step. And then we add some independent noise on the X and the Y coordinate. So if I was the identity matrix, essentially we will have a random walk on this space. And essentially you can see how the constraints are. The only constraint is that you need to stay inside this box. So you have essentially a box constraint. So what about the sensor? These are our decision makers. And essentially they get noisy measurements of this sort. Essentially you take a linear combination of the X and Y positions of the target. But these observations are corrected by noise. Observation noise, and so on and so forth. So for those of you that may come from a different formulation, you can think of it as a state space model. So this is your state equation, and this is your observation equation, and you don't need online optimization. You can formulate the problem from a state space perspective and sort of try to solve it. But it's a nice and neat illustration. And this epsilon VC is the indicator vector because it means that, for example, a sensor position over there, if the target is positioned over there, it may return a zero measurement because the target was too far from the sensor. What about the objective function or the cost function for every sensor? Essentially is square error loss. What is your measurement? And essentially you're trying sort of to identify the position. So this is your decision variable. And of course, it's the expectation because there is a lot of randomness, as I mentioned. There is randomness with respect to the measurements because there is noise, and also because of the random type of work. And this is the global cost function. Target detection problems or target tracking problems, again, 50 years of literature, but nevertheless, it naturally falls into, or you can describe it in this framework. Nothing prevents you from, yes. Sorry? No, it's moving, no, sorry. The target is moving according to these dynamics. So I'm here, and as I said, if A was the identity matrix, you will be doing a random walk. Yeah. So then you can start thinking of generalizations. Actually, in this paper, they were also considering velocity. So then the decision, the xt, doesn't only give you the position, velocity that you move on the x and the y coordinates. So automatically then it becomes a four-dimensional decision problem. So you need to solve for four variables. You can have colored noise, correlated noise. You can start turning the crank and make the problem more challenging. Okay, something different. I'm just talking about support vector machines just to put it in a very clean mathematical formulation. You can think of your favorite machine learning model, including neural networks. And here, you can put a multi-layer perceptron or, a convolution neural network. All of them fit into this framework. And that's why, especially because of the applications to machine learning problems, this framework has attracted so much interest in the computer science and machine learning type of community. So there are M decision makers or M agents, and each one has access to observations that are becoming available in a streaming fashion. So think that you have a data set. In principle, it doesn't have really to be a dynamic environment, or it can be a really streaming setting. But essentially, there are TI observations, and at every point in time, you see or you process from your database one observation. And essentially, you have d-dimensional features, the covariates, and the class label +1, -1, because I'm putting the support vector machine framework. And essentially, this is the decision function for support vectors. This is the indicator function, and so on and so forth. And essentially, you're trying to find the weights to solve the support vector machine problem. And the global function is, in this case, you are taking sort of the average, which if you translate everything here, there are no constraints. So essentially corresponds to constraint-based decision online optimization. So in principle, if you change this to any other machine learning of interest and its corresponding objective function, basically any machine learning problem can be subsumed in this framework of distributed online optimization. Let's switch gears. This is, again, a very old topic. Nash Cournot games go back to almost classical economics. Definitely the economists have looked at it primarily in monopolistic or duopolistic markets and so forth. So let's see how the story goes here. I have n firms interacting through some communication network. And essentially the constraint set corresponds to production and market capacity constraints that firm I faces. And then the cost function or the regret function or the objective function, in this case, becomes a profit function for not form, but for firm I at time t. That depends on time varying functions, factors such as production cost and the product's price. Some things that Roberto was mentioning yesterday with respect to hotels and so forth. So essentially, the decision variable for the firm is how much to produce at time t. And this is a demand function. So these are some time varying coefficients. You see that the demand is sloping downwards as a function of the quantity. And here, the total quantity that can be produced is the sum of all the quantities that the end agents or the end firms are going to produce. And essentially, so here, essentially you have, depends on how you formulate it, you have an online type of game because how much you're going to produce also depends on the decisions of everybody else, and you are in a non-cooperative type of framework. Potentially, if you were having a cartel, then you can make it in sort of into a cooperative type of game. And then remember that we had a formulation about multi-agent cooperative optimization. Then you can turn the problem into cartels that are in many countries illegal. So a few things about communications in this framework. I'm going to say a few things about the communication graphs and some new directions that people may be interested in pursuing. So many different settings have been considered in the literature. The graph can be undirected and fixed, so it never changes over time. So we have set our communication network and how we communicate the M agents, N agents, and we don't change it. We can have fixed directed graphs. I communicate with Panos, Panos communicates with Roberto, and so on and so forth, but not vice versa. We can have time varying or switching directed graphs, and some recent, very recent work, people said, okay, why don't we go to random switching graphs? From an algorithmic perspective, this is the easiest to analyze and especially say something about the algorithms. From a theory perspective of how the regret grows, actually, this is a very hard setting. This is much easier. And don't ask me exactly why. Having read the papers, I still cannot put my finger on why one type of theoretical results, this becomes easier. For saying something about your algorithm, this, I mean, you can easily see if the graph is not changing, it's easier to say something about the behavior of the algorithm, but in terms of rates of growth of the regret is much harder. This is the predominant paradigm. You have full information. So essentially, once I make my decision, I pass it to my neighbors. Then they decide to do something with it. And of course, as you can see, the last 2-3 years, people start saying, well, if we are really dealing about privacy preserving settings, I'm not going to pass exactly the XI, and they start borrowing ideas from differential privacy, essentially by jittering or adding noise to the XI, to the decision variable, and then, again, very open, very recent results, very incomplete results. Something else, again, that people have just started considering is what type of transmissions are we going to have? If you go back to the tracking problem, this is very common in sensor networks. In principle, we can have all the decisions to be made and transmitted on a fixed clock. Every 5 minutes, the sensors wake up and communicate with their neighbors and give the latest measurement that they got. Or we can be on an asynchronous clock. And therefore, I made a measurement right now, and I'm going to send it to Panos. But Panos doesn't want to transmit because he may be short on energy resources. So maybe he has a solar cell and he's trying sort of to accumulate enough energy in order to make a transmission. 99% or 95% of the literature is on a fixed clock, a fixed schedule, synchronous type of transmission. The moment you start putting asynchronous transmissions, unless you have very simple settings, life again becomes easy. Okay, so what about algorithms? How you solve these optimization problems? Gradient, subgradient, so gradient descent, and it's stochastic Counterparts, stochastic gradient descent. This is the dominant paradigm for solving training neural networks, are sort of extensively studied, but also the other paradigm that has been looked at, and as again you can see, it's the business for the last 2 years, maybe 3, gradient flip methods, zeroth order optimization. Actually, zeroth order optimization suddenly has become, if not the flavor of the day, but a very, very active area, and what type of results you can prove, and so on and so forth. Okay, so here comes, so there are, in the centralized online optimization, when you have only one agent, obviously there are 2 types of theoretical results that you're going to sort of prove, especially if you assume that your cost functions are convex or even strongly convex and maybe smooth. First, that the algorithms converge. And the other type of theoretical work is how the regret grows as a function of the horizon. If you remember, the regret is how much is my cost, or the cost of the n agents, versus a comparative sequence that in some sense depends on exactly on the setting, has some oracle properties, it's the true minimizer and so forth of this finite horizon problem. So in the convex case, you see that the regret grows at a sublinear rate, and therefore the normalized regret, if I divide by t, essentially vanishes as a function of time. For static regret, I can do much, much better, because essentially I can do as well as n of an oracle by paying a very small price. With dynamic regret, and again, convex functions, essentially I have this rate, plus this is a long story, in the sense that this thing starts depending on exactly additional assumptions that I put on the communications graph. So because it's the nature, that's why I said that the static regret may be kind of a little bit simplifying, but allows you much sharper analysis. And then in the dynamic regret, in the strongly convex, essentially the only thing that you pay, which is a function of time, is this difference, the rate of between the optimal sort of decisions at every point in time. So essentially, this is the oracle type of cost, and essentially, although you're not the oracle, but you're solving this problem, essentially you don't pay anything more. Okay, so a couple of comments. These rates match their counterparts from centralized online learning. When it comes to inequality constraints, for equality constraints, there are some results in the literature. The rates are significantly worse. For inequality constraints, pretty much the topic is fairly open. So as you can see, there are a whole bunch of interesting open problems for those theoretically inclined. And for, as I've already mentioned, for dynamic regret, and especially if you start having constraints and time invariant graphs, there are no results in the literature. And again, as I've already mentioned, if you have directed graphs, and these are undirected as well, directed graphs, some results can be established, and I cannot really put my finger of why that is a little bit of an easier case. Okay, in the last 15 minutes, let's switch a little bit and talk about some gaps in the literature. As you can see, in the existing literature, there is nothing about non-convex case, and can we say anything about it? And then also about some other types of algorithms. So many of you may have seen some flavors of these algorithms, because that's why I asked the previous speaker what type of algorithm his team was using to train the neural network. And the vanilla answer is always stochastic gradient descent for the usual reasons. It's well researched and so forth. However, stochastic gradient descent has a very, very slow rate of convergence. Probably so. And essentially, stochastic gradient descent is a flavor of Robbins-Moreau from 1950. So Adam, this was a paper in 2014, started thinking of using information from past gradients. So these are called adaptive gradient or adaptive momentum methods. And suddenly it has already 5,000, 6,000, 7,000 citations, because essentially Adam and all the other versions is exactly what you're going to find in TensorFlow or PyTorch. You can always ask for stochastic gradient descent, but given all the shortcomings of stochastic gradient descent, of how slow it's the rate of convergence, people have switched to those. Adam didn't come with theory, he just came with a beautiful idea, a lot of experiments, and then people started tweaking and digging deeper and proving that even in some trivial settings, Adam will not converge. And then they started looking at all these versions. Okay. What is Adam or Adam type? Essentially, you generate a sequence of iterates of this form. So MT is, let me jump a little bit. If I take MT to be the gradient and VT the identity, essentially I have gradient descent or the stochastic gradient version. And as I said, this goes back to Robbins-Moreau. It's probably older than most of us in this room. But right now, essentially what the idea was, and I'll show you a few more details in the table, was instead of just using the latest gradient, let me keep a short sequence of previous gradients, take the average, so keep a little bit of history, and also similarly for VT, and we're still talking about first order methods, don't think about Newton here, and we'll see how this is updated, and essentially try to get better updates. And of course, you have the step size is always there, the step size is always a big headache, and so on and so forth. Again, why SGD is not a preferential method? Because theoretically, we know that it has, the step size needs to decay to 0, and especially when you're solving for 8, 50, 100 million parameters in a neural network, you don't want to do that. And we saw some very nice real examples before lunch. So the key idea of adaptive methods is to choose averaging functions appropriately. So the name of the game is to create these VTs and MTs and so forth. So John Ducci, even before Adam came up, he was thinking more about online optimization and proposed, you see, to keep this type of updates. And of course, his step size became 1 over square root of t. And especially when the gradients are sparse, because you have a lot of sparsity in the problem, it provides a significant improvement in the empirical performance of gradient type of methods. Okay, so right now what I would like to pitch is a distributed version of Adam, and it's going to start giving you some insights. So I'm considering cost functions, but can also depend on auxiliary stochastic variables. I have, this is the adjacency matrix of the network of my agents. And there are all these tuning parameters that this is the step size, but there are a whole bunch of tuning parameters. So what do? You first take the gradient at time t. Then you take a linear combination of your previous history of averaging. So essentially this is kind of a moving average with appropriate tuning parameters of previous gradients plus the new gradient. Then you take essentially, if you look from Ducci, something akin, this is element-wise multiplication, and you keep another sequence, then you take a third sequence. So people have gone into this sequence production by putting additional terms that try to capture various aspects of the history. And of course, in the end, somewhere you need to communicate. So this is the communication step after we have our update. And then potentially to satisfy constraints, we may have also to do a projection. So let me describe this in words. So essentially, the decision makers exchange local updates. Each decision maker computes its gradient, as I already mentioned, and then all these called moment vectors, because essentially, they keep the same history. And at some point, you update the new estimate by first computing the average of the neighbors' decisions. Depends on how you communicate, what are the communication paths, and so on and so forth. And that's how you do sort of your update. Actually, this is a very generic scheme and depends on how you pick the beta, beta 1, beta 2, beta 3, beta 1 is kind of a sequence as well. You get into, I don't know how well you can see, you get into this zoo of methods. So this is the generic Adam, and these are the centralized version. So this is SGD, stochastic gradient descent. This is Ducci. Somebody came up a little bit later with RMS flop. This is Adam, but with a little bit some variations. So this version converges as opposed to the original paper. This is Rachel Ward saying as grad. This has in some sense the best convergence rate. So essentially, you take this zoo of various variations of Adam methods, and with a little bit of work, we turn them into distributed versions. Okay, what can we prove by using, so these are essentially better methods than stochastic gradient descent. Don't get me wrong, you could have used a whole bunch of other algorithms, as I mentioned, either based on gradients or subgradients and so forth. But these adaptive momentum methods have become very, very popular, converge fairly fast, they are fairly robust. And that's why, as I mentioned, if any of you that use either TensorFlow or PyTorch to train any neural network, you can specify which flavor of Adam-like method you would like to use. These are the centralized ones. So more or less all these available in the existing TensorFlow PyTorch infrastructure. Okay. What about the convex case? We are in distributed online optimization. You need to start making some assumptions in addition to convexity, but the communication graph is doubly stochastic. Row sums, column sums equals to 1. This is stronger assumption than the centralized case. If you look at the literature on the centralized case, it only requires bounded L2 norm of the gradient. And essentially, as you can see, under only feasibility constraints, no inequality, we don't know anything about that, is essentially the rate that I described with the classical gradient type of methods. This term depends heavily not only on the structure of the communication graph and the number of agents, but the structure as well through its second eigenvalue. We had a talk in the morning about, given the fact that the matrix is doubly stochastic, the first eigenvalue is trivial equals 1, and therefore the spectral gap plays a very important role on this term. Non-convex case, okay, I need to start piling up assumptions. These again are borrowed from the centralized versions. So I need to have Lipschitzness on the gradients and bounded cross functions. But here, nobody has ever proved anything about the full dynamic regret. Essentially, the localist, remember at some point I talked about adaptive regret over a subset of the time points, then that's up to this point, that's the only result that we have proved, or we were able to prove under feasibility constraints, and that the length of window that I'm considering is sublinear. And therefore, essentially, I get this type of rate plus an extra cost again, as before. Okay, before I show you some pictures and wrap up, something that this is maybe, no, actually, I haven't mentioned this paper. This guy has done other work in his co-authors in distributed online optimization. This is a very, very interesting paper in the SciAm Journal of Optimization. And actually, when I first read it, it came to me as a surprise. So the decentralized algorithm obviously have more restrictive assumptions. I already mentioned some of those. And typically, I didn't mention anything from a convergence, from algorithmic convergence rate. I focused a little bit more on the regret. but have worse convergence rates. And this guy, what he said, and I'm going to show you the scheme, introduced essentially a correction step, because what happens in this decentralized gradient descent, you start accumulating a few errors that you cannot really get rid of, and essentially that's why you need the correction. And therefore, for decentralized gradient descent, not the stochastic version, full gradients, he provided a linear rate of convergence for strongly convex objective functions. That was not possible in the decentralized setting. So essentially, he recovered the classical results from centralized versions. So what do you do? Remember that essentially, these are the various momentum functions, and this is the solution. So I put it in this form. And then let me denote W hat as this is the adjacency matrix of the network. And I add the diagonal and then divide by 2. Okay. Equation 14.8 is essentially the Adam step, the update rule. And then the previous step, I write it in this very funny way. And the only thing I'm going to say is that if you were in stationarity, because W is a W stochastic matrix, X equals WX for the optimal solution. And it comes from that when you let the iterates go to infinity, and that's why he rewrites it this way. The rest is algebra. You know, you do all these manipulations, you write all this difference, you get a telescopic sum, and lo and behold, essentially the corrected version, both of Adam type of methods, even you can do that with stochastic gradient descent, essentially takes this form. So instead of using the W, the communication matrix, we use this variant, plus you carry all this history, this small deviation. And essentially, for full gradients, essentially that establishes in a decentralized fashion, for strongly convex objective functions, the linear rate of convergence. So this sounds kind of magic until you go to infinity, you know, infinite number of iterates, and you do that type of analysis, 5 lines, and it's easy to see in his paper. Why does this correction step matters? Okay, so some empirical results, and I'll wrap up in 2 minutes. So I have streaming machine learning, support vector machine, softmax regression. This is the MNIST data set with the indices. There's some other data set. What do we see? Distributed SGD, vanilla distributed Adam, but with appropriate choices of the tuning parameters so that it has convergence. Here we correct it with this correction update with distributed version of stochastic gradient descent that exists in the literature, and then we have this correction. It shows what can we learn. First of all, we learned that the correction matters, and matters a lot, and it's in a lot of these problems. And of course, adaptive momentum methods are much better than SGD. That's why right now in TensorFlow and PyTorch, nobody really uses the SGD. Always the default is to go with an Adam type of algorithm. And some additional results. CIFAR 10, it was discussed in the morning, 60,000 images, 10 classes, 2 neural network architectures, ResNet, 48 convolutional layers, 1 max pooling, 1 average pooling, DenseNet, 40 layers, I don't know how many million parameters. And this was trying to fix the ResNet. This is completely relevant to this talk, but DenseNet was trying to fix the problem of vanishing gradients that the ResNet architecture suffer from. And also, we applied the data augmentation. So essentially, data augmentation, you take the picture, you put it in a bigger setting with more background, and then you start shifting or rotating your picture in order sort of for the network to learn the invariant aspects of the picture. 10 agents. And what we did was both homogeneous and heterogeneous distribution of the images. So homogeneous, it means that essentially I have 1,000 airplanes, 2,000 cats, and I split them homogeneously across the 10 agents. Heterogeneously, I put more cats on one agent, fewer airplanes on the other, and so forth. Test accuracy and also execution time. Essentially, the decentralized versions are much, much faster. The Adam type of methods are much better than SGD. By now, I'm just preaching to the choir because this is very well known in the literature. You see that the moment you start doing imbalanced distribution of the classes across your agents, you start paying a price. So these are some results. But dense net, more or less, what you can see is much better as a neural network architecture, much higher rates. Some comments, more or less, I think this is an important takeaway lesson. And this came really as a surprise, and people have started sort of utilizing this type of corrections extensively. Okay, some future directions. Okay, you start always with first order methods. Then you switch to zeroth order methods, no derivatives, and so forth. Second order methods are expensive, but they have much better convergence properties, Newton and all its friends. So there is some definitely work in centralized online learning. Nobody has tackled the second order methods. The problem is how are you going to communicate the Hessian? The Hessian is expensive, how much information you would like to set, and also depends on the nature of the communication graph. It may start screwing you up. That's why, at least you can always use it, but from a theoretical perspective, you want to prove something, that's where the challenge comes. All the results up to this point is Euclidean space. But in many other settings, you may want to consider manifolds, Riemannian type of manifolds. They come up in deep learning, principal independent component analysis, no work to date. Deep learning, actually, there is the latest flavor in the last 2 years is essentially do deep learning on manifolds, and even the next step is on nonlinear operators in order to get the invariant geometric features of your data. Lack of any theoretical results for online games. So everything was in the more vanilla setting. Lack of any theoretical results for competitive ratio metrics. Few theoretical results for constraint problems. So all these are very, very open areas. You're welcome to contribute. Thank you very much for your attention. Yes. I mean, how many are computer scientists? Because I'm gonna maybe make a somewhat of a comment here. As in many areas of science, a lot of ideas that have been well studied in one area, suddenly they're rediscovered, repackaged, and the original paper has 300 citations, a new flavor of repackaging because it's a much bigger domain, especially with deep learning, has 5,000 citations. The world is not exactly fair, but that's a general comment, but there is a lot of repackaging. But there are also some new results, you know. And especially all the analysis more on the regrets and the rates of growth. The classical optimization literature never thought from that perspective. It was much more convergence of algorithms. So, you know, as a community, we keep learning. But as I mentioned, that's why I kept emphasizing a lot of these problems go back 30, 40, 50, 60, 70 years with a lot of. Yes, exactly. Exactly. Yeah.
We apply it to networks.
You can see what type of performances you can get. I mean, these are not trivial data sets. And you run this on an 8-core. This was run actually on an 8-core laptop. Okay, we had 10 agents, so there was a little bit of latency. But essentially, in 20, 30 minutes, you can train these networks, have, I don't know, 8 million, 10 million parameters. So, yes.
I'm just curious. I see the time performance here. Usually, computer science performance relevant because of the machine using. You always measure it in terms of input size. I was wondering, like, if there's any calculation done in terms of input size?
As a function of, sorry?
Data, input size, the data size. Easy.
Um,
That is relevant.
yeah. I mean, this is a 60,000 images, so this is the number of observations. Here you do essentially, we did 100 epochs, and essentially the training was on mini batches of size 500. So that's what T evolves over. Classical. Yeah, if we had on the Florida supercomputer, probably it would be 5 minutes with a similar architecture and so forth. Yeah.
Well, I don't really. Yeah. I wanted to ask you how the structure of the problem enters in the regret. Because, for instance, the dimension of the decision space, the dimension of the because it enters the N value, the capital N value.
No, capital N is the number of agents or the number of players.
The number of agents, yes, but not the dimension of the space.
Oh, the dimension comes in. It was.
We have a slide with the 4 basic coordinates.
Enters xi is this is the dimension of the decision variable.
Without guessing to the regret, there is a slide with different regrets for. Yes. Okay, anyway, it's fine.
Yeah, because essentially here these are scalars because you just map to R1 and essentially you just sum over the agents. So it's total cost across all agents minus the total cost of the comparator sequence. So it's a number.
And there is usually this thing, what I do, there is a clear distinction between parameters and data.
Yeah.
And it's the center and very much into, for instance, automated machine learning. But still there are influential
yes.
minority who really think that with your method that you could mix up.
Yeah. So here
the distinction between parameters.
Yeah. So here in the support vector machine, essentially these are the weights in the quadratic programming and so forth. In a neural network, there are in the neural network, essentially, again, depends whether you're going to consider as part of the F or only the weights are your decision variables and you fix or you do something else in an additional loop.
The weights you can have.
Yeah, the weights correspond to this, essentially are the decision variables. Yeah. So the hyperparameters, in principle, in these formulations, are not directly taken into consideration. People use maybe fixed sequence of hyperparameters, or they do some grid search and they solve the problem over a certain grid of hyperparameters and they pick the best one. So it's not directly. In principle, you can, as long as you cook up the right objective function and you incorporate it. So, this is not going to be your cross entropy loss, let's say in a neural network, but you put maybe an additional term that optimizes over the hyperparameters. In principle, you can do it in principle.
By level rate.
By level. That's the new frontier, and a lot of these guys are moving to bi-level programming. We have started seeing the first type of problems exactly for this reason.
What they usually they do the a posteriori analysis.
Yeah. Exactly.
Data, then they learn from that to the online.
Yes. Yeah.
So this is the typical.
So exactly because of your question, the community has started thinking of bi-level programming type of questions in order to incorporate the hyperparameters. Here, they are not really explicitly incorporated.
But the C plus bi-level is.
Yeah.
Any other questions? Let us take Jones for next.
Sorry, I took half of the coffee break.
Very nice. I don't know if you work online.
It's sexy. COVID exercise, trying to learn.
If I don't look so much, I think we can online do. I'm semi-extensive. Very interesting.
Really practical.
I'm not really like it. Because online. Maar how you do it, they should. It's not easy. Yeah. It's tough. This is good. Kijk, staat hier.